Hi everyone, we are back. This is week 2, 2020. We'll have only NA, if you remember from what we discussed last time. And let's start. So last time we started to discuss the issue of having a density of states which is different to the common parabolic bands, and we started to look into the Gaussian density of states. And we saw that there is more than one way to define the band edge. And really, what is the correct band edge is going to depend what you're going to use this edge for, because there is nothing here which is clearly better than the other. And as we all know, finding the edge is a centuries old problem. So how are we going to tackle this? Basically, we ask ourselves, why are we looking for the band edge? Because if we have this Gaussian density of states, here the full width half maximum here is 3 kT, which is around 75 milli electron volt. And we can apply the full Fermi integral over this density of states and find the relation between the charge density and the position of the Fermi level relative to the center of the Gaussian density of states. So really we don't really need anything like the band edge. However, we don't really want to use the full Fermi integrals, because it's much more efficient or easy to use the Boltzmann statistics. So really what we want is to use this expression, and we want to define EC in this context. So really what we are interested in is the region where we have this exponential growth or in exponential decay, and we can see where this Boltzmann approximation is going to hold. And now we need to define the parameter that would fit this line. So we place here another horizontal line, and we can graphically define the position of the band edge, and we see that in this context it's a little bit below minus 0.1 EV. And if we do it more rigorously, it is possible to show that depending on the width of the Gaussian, the real effective band edge is going to be shifted downwards by sigma squared divided by 2 kT. And just to place everything in context, I've overlaid here the Gaussian. So you see it's somewhere below the middle of it. It is important to remember, just as I said before, this is not the right way. This is the way we chose because I believe it is the most appropriate one when we are thinking of semiconductor device models, simply because in most models this is what is being used, the Boltzmann approximation. It doesn't mean that it is easy to find this band edge. Of course, mathematically or graphically it's easy, but if you are doing experiments and you want to find the band edge, it's extremely difficult, and it's very hard to find anything truly reliable in this context when we are talking about organic electronics. As always, we've also had one assumption here at least in order to define this right or effective band edge, and I leave it to you to find it. So I hope that by now you know if someone asks you about organics or what you think about organic electronic, this is the reaction you are expected to show. But really, at least at the beginning, and sometimes it might happen even now, people look at organics and they see that they are very different, and they see mainly the obstacles and the challenges. And really many people miss the point that obstacles are really misunderstood the new opportunities. And in this case, it's really a true thing, because the problem that organics are non-crystalline, that's why they are flexible. They are organic or polymers, so they are soft materials. You can print them, you can do easily large area electronics. So there are really new opportunities, and finding the right ones is really still a challenge. And it's true, silicon processing doesn't really work with them, but by now we all know how to work around without using silicon processing procedures. So really what we are going to do next is we are going to try and understand the physics and chemical physics of these materials, but in the context of devices. We will try to understand all the things that we need, and hopefully I'll manage not to involve you with the things we don't need, because really the idea is that we will focus on understanding the devices, and will not get lost by the fact that there are zillions of processes that may take place in the organics, but most of them are not going to affect the performance of the device. So within this course, we don't really care about them. Although sometime in the future, if you will go into more details, you won't be able to manage without expanding your knowledge. But we won't do it here. So before we continue with the device chemical physics or the semiconductor itself, we need to remind ourselves a bit about contacts, and it will be a good opportunity to discuss what else might be missing when we are talking about contacts. What are we going to assume? What is there in the textbooks that no one ever told you about and it's critical? And basically, most of the details I will discuss in the following slides. We are not really going to use them in detail in the course, but it's more for you to know and practice what it means to have a model that looks like it was given in Mount Sinai, but really it has lots of assumptions behind it. So let's remind ourselves what happens when we have a metal which has a given work function, and a semiconductor, which in this case the Fermi level is somewhere close to the middle. And we are going to make a contact between these two. So we see that at the interface itself, there is a perfect alignment between the levels of the semiconductor and the levels of the metal. Once the two make contacts, we see that the Fermi level and the metal is higher. So what will happen is that charge will flow from high to low, and we'll get this kind of charge transfer from the metal to the semiconductor. And this will of course induce a shift in the Fermi level, and the charges will stop flowing once the Fermi level is constant across the interface. And you've noticed here that there is this mismatch between the Fermi level and the conduction band, and in this case we'll call this an energy barrier, which is marked here by phi b. So basically what we did here, we assumed that we are interested in the energy levels under equilibrium conditions, and in that case we waited long enough until everything stabilized and there are no currents in the system, and the Fermi level is constant. So this tells us what's happening close to the interface. And the question is, what about the the energy levels or the bands, how would they look like when we go far from the interface. So basically what we usually do is we say that when we attach two materials to each other, then there is this interface where they are touching, and close to this interface there will always be some kind of interference or some kind of effect between the two. But if you go far enough, all the interference will decay, and far enough from the interface, the semiconductor doesn't really know that there was a metal on the other side. So basically, the Fermi level is supposed to be at the same place relative to the conduction and valence band as it was before we made any contact. So we know where the bands are going to be far from the interface. We know that we place them close to the interface really the way they were before, and that's how we created this energy barrier. And basically what we need now is to connect the dots, and basically this is what the bands would look like. And of course we are not really solving here everything to show exactly why there is this bending on, or how to follow the exact function here, but you've seen it in other courses. And of course one of the basic things we'd be interested in is what is the charge density that this contact has induced inside the semiconductor. And to do that we need to identify the fact that what the contact did is dictate the Fermi level close to the interface, and it is phi b below the conduction band. And in this case we can use these statistics, and we assume that we can use the Boltzmann statistics, and this way we can immediately derive the charge density, which is the initial conditions in space close to this interface. What did we assume, or what did I assume while going along and presenting this? First of all, I aligned at the interface the two material as if there is nothing that would cause a shift, and that means that we assume that there are no dipoles formed at the interface. And also we assume that far enough where there is really no effect of the interface, this far enough is still within the device, that we can really use it as the second boundary condition. But sometimes devices are small and this doesn't really hold, and we really need to solve and consider the contacts on both sides, or to find out what are the conditions at the other interface which we have ignored so far. So if you like, graphically we can look what will happen if far is too far, and we just do it like that. And if a device is short, we often will have a situation where the bands seem to be straight. And this is one of the effects when the devices are short, but more importantly would be the effect that we'll have to consider the boundary condition at the other side. I think you've seen it in other courses when you've looked at p-n junction or short and long junctions. This is really similar considerations. So really this is another point where it's good to remind ourselves that we are going to have assumptions all along. Hopefully I'll remember to mention all of them, or at least I'll intentionally intentionally not mention some of them, so we'll have something to discuss when we meet. So let's look at this picture again. Again, we have here the metal, we have the semiconductor. There is something in between that separate them. And we've already seen what will happen in this case, but now we want to ask ourselves what will happen if the metal work function is outside the semiconductor band gap. What would happen? If we remember what we said before, then charges would flow from one place to the other to equilibrate the Fermi level. And the question now is, if since the metal is above the conduction band, and if the Fermi level would simply be extended like that, then we'll have a metal. So really what's going to happen when we apply these two and make them touch each other? From before we can assume that when the two touch there will be a lot of charges spilled into the semiconductor. The question is, will they be spilled enough to make the whole semiconductor metallic, or are they going to do something only at the interface? And basically what happens usually is really a lot of charge accumulate at the interface, and because the density is so high, it creates band bending, which is very steep. And basically we arrive at a very thin layer where the bands are really bent very sharply across. And many times we ignore all these details of what's happening here. And what we do is we say that when we try to place the metal above the conduction level, or the same would be if we try to place it below the valence band, is that a dipole is formed, and the dipole is simply the charges that accumulated at this interface, which have left the metal. And basically this dipole or these charges, they pin the contact at the conduction band. So really the contacts effectively cannot be outside the bands. And we'll talk in further down the course, they usually are even pinned lower than that, even if there are no special defects at the contact itself. Speaking of that, let's look at the heterostructure. Now we have our semiconductor, and we have here now a low band gap semiconductor here in the middle, close to where the metal is going to make contact. And the question is, would this metal going to be pinned to the band, to the conduction band of the low band gap material? Or we could ask ourselves how wide or how thick this layer needs to be in order to be significant and to pin this metal. So we've seen what happens when a metal touches the semiconductor. We also touched at what might happen if there are some interface states. And we would like also to look at what else might be happening when we have this metal touching the semiconductor, and we'll look now very close to this interface and ask ourselves what else might be happening here close to the metal. And we are going to place a charge here and ask how it's going to be affected by the presence of the metal. So basically, here is our zoomed picture, and we're going to place a charge, and the metal is now a perfect conductor, like a perfect mirror. And if we solve the potential of the charge close to a perfect mirror, then the solution would give us the equivalent of an image charge. And if there is a minus charge in front of the mirror, then it will be imaged by a plus charge on the other side. And the reason we have this plus, because we know that a metal doesn't let the electric field penetrate, so in order to fulfill the boundary conditions here for the electric field, there is an effectively positive charge generated on the other side. And the question is, how would the energy levels or the potential of the electron going to be affected by the fact that we have a positive charge nearby? And really we can use zero order intuition, and we know that when we have a pair like that, plus and minus, they would attract each other and stabilize each other. And whenever there is a stabilization, we know that stabilization implies a lowering of the energy. And from that we can deduce that we should expect that the energy of the electron, which is represented by the conduction band, would be lowered because of this image charge. What we'll do next is we'll try and put some numbers and formula to see how it is really being lowered and what the shape is being formed. So what we have to do to calculate the potential that is being induced by the positive charge is we start with the force between positive and negative charges, and then if we want to translate that into a potential which is associated with bringing it from infinity, so the work that's been performed is for this integral, which just like physics 1, I'm sure you've seen it before. And from this we see the potential that is going to be induced by the image charge. Of course, the conduction band, which is the potential that was created by the lattice or all the other atoms that around the electrons, is going to be there as well. So basically what the charge would now see is the linear combination of the two. The band, which is the material, and the image potential, which is due to the presence of a metal that creates an image charge. Why do we care? We'll see in a bit. So we'll visually build the picture of energy bands and the image potential. And we'll start with a standard 100 nanometer thick device. We have here the contact. This is the conduction band. So there is a 0.5 EV injection barrier. We're going to apply a bias and see how the bands are tilted as a function of applied voltage. And this is nothing new. It's the standard tilt in the bands that reflects the electric field, which is the derivative of this band. Next, what we'll do is we'll add the image potential, and you see that the overall potential now is in red here. The blue is reminiscent of what we had before, just as a reference. And what we will follow is the maximum potential, which is the point where we will reach the maximum. And at first it is at the end of the device, but then it will gradually move towards the contact, and this would reflect the barrier lowering, which is actually the peak of the red curve. And you can see how the barrier lowering is going up, and really at some stage all the action is really on the nearest nanometers close to the contact. And finally, to see better what's going on, we'll zoom in on this region, and again the same picture, only now it's clearer. We see this top of the potential, which is really the height that the charges need to climb. So if when we started they had to go up by 0.5 eV, now you can see that all they need to go up by is 0.5 minus 0.15, which is 0.35, right? And that's the whole idea. And this picture really summarizes it all. We have here the work function of the metal, the energy bands once we have included the image potential, and all the other notations that are often useful. So as I have said several times by now, the material that I deliver or the slides themselves are not so important. The idea is to think a little bit and try to see what assumptions are there. And for example, one of the questions is why should we care about this image force that is being produced by a metal? Because if we are really going to solve devices, we're going to use the semiconductor device model. And in a semiconductor device model, we have all the equations we need, right? So this is like the semiconductor. We have two contacts. We have the continuity equation. We have the Poisson equation. And we know the Poisson equation is taking care of all the charges and the potential that's being generated due to the charges, and takes into account the boundary condition on both sides. So why do we need something extra? What's wrong with this that we need to make corrections? So why did we introduce that correction? As I said, we have basically all the equations, and really to look for the reason, you need to look again at this picture and see that we are really solving a three-dimensional device using a 1D equation. And we need to ask ourselves, is it okay to use a 1D to describe the 3D problem? And while we ask that and try to answer it, we'll really discover why we need to introduce that correction of the image force. So basically, when are we allowed to do that? So of course, if no one is seeing, you can do whatever you like. But from a more mathematical point of view, we know that if the other derivatives are zero, or that everything is constant in the other two directions in the plane of the contacts, then it's okay to think of the problem as 1D. Is this problem always 1D? That's really the question. And what situation may make this problem different? Let's look at the charges here. That is really just an illustration, but nevertheless, if we go close enough and we are interested in the dimension of the distance between these charges, then really on the scale the charge density, then of course the system is not uniform, because you see a charge, there's no charge, and then you see a charge again. So in that case, the assumption that we can use a 1D equation breaks. We really need to take into account the fact that we have separate charges when we are getting really close to the metal. So really, if we are interested in what's happening pretty close to the metal, and that's where the injection barrier is going to be, then we really need to account for these separated charges. So really, when we are using the image force potential, we are saying that we have a charge density that is not too high, and on the scale of the distance between the charges, the system or the device is not uniform in Y and Z anymore, and instead of now solving it in 3D, we solve it in 1D, and we introduce a correction which takes care of this non-uniformity. Of course, this is again an approximation which works well when the charge densities are not too high. So we go back to this picture that I've shown you before, and we've discussed this image force and the issues that I've raised in the previous slide. And if you paid attention to what I've said, you probably missed the reason why this picture is wrong. Because what we did is we drew this line using this potential, and this potential assumed that the charges are really separated, so the charge density is not really high. And really, if we draw the potential like this, it means that the charge density here close to the contact is going to be extremely high. And if the density of states, the full density of states here could be 10 to the 21 maybe, then of course this is a range of 1 nanometer. And again, that means that beyond 1 nanometer, the whole picture of the image force doesn't hold anymore. So really, one should use the image force potential with care. And remember that it is mainly useful when we have a high injection barrier and the charge density is low. So we are practically done with the contacts and the effects that may take place close to the contacts. Since this is a basic course, we are not going to handle cases where these strange things are happening. You won't need to try and understand if when you are solving a problem that you are interested in, if the image force can hold or not hold. Most of the time we'll simply ignore it, knowing that we have made some kind of an approximation. Some would call it a mistake if you like, but as long as you are aware of what you are doing, all the assumptions are clear and understandable by you and those you show what you do to, then I think we are okay. So now we are ready to move and look at the transport of charges and the JV characteristics of devices. And that would be in the next PPT.